So today we'll discuss more preliminaries, and we will begin with a discussion of the proof technique of induction, which is useful and oft put to work. So that is the first thing on the agenda, and then we'll talk about cardinality. Okay. So the principle of induction is the following. We are interested in a certain sequence of propositions depending on an integer. And so we suppose that the following are true. So we suppose that some sequential number of the propositions are true. So p at n naught is true, p at n naught plus 1, up through p of k. Okay, so some number of these propositions are true. And also the following is true, that if some sequential number of these are true, p of n naught through p of m, where m is bigger than or equal to k, then p of m plus 1 is true. So in other words, so we think about it this way. So start with m equals k. So from the first one, we know these n naught through k propositions are true. So the second one then says that these being true, they imply that the next one in line is true. So number 2 says that these sequential propositions being true imply that the next one is true. Right, so these imply that we have this next one. And then now we have, again, a sequential number of propositions that are true from n naught up to k plus 1 now. So my m now is k plus 1 instead of k. And so now the same logic with these propositions implies that the next one in line is true. So we have p of k plus 2. And so all of these now imply that. And so we would just keep sort of iteratively applying this logic to these sequential number of propositions to get the next one. And so the inevitable conclusion is that this process continues. And so p of n is going to be true for any n bigger than or equal to n naught. Okay, so basically what we have is we know some sequential number of them are true. And if we also know that that sequential number being true implies the next one, we get this cascade effect, wherein everything in line after p of n naught sort of gets knocked down. And so you may remember that these, in number 1 here, these ones that are true are called the base cases, and this in part 2 is called the induction step. So basically, you have a bunch of propositions you want to prove. You prove that a few of them are true, right? A few of them in a row are true, and that if you know that some of them in a row are true, then the next one is true. Okay, and if you can do those things, then it follows that all of the ones down the line are also true as well. So that's the principle of induction. And we will go over a couple of examples to sort of remind you of how this works. So most commonly here, you only have one base case. You establish a single base case, and then you show that if you know that one proposition is true, then the next one has to be true. So that's a bit those are sort of simplifications of these steps. These two are say that this principle works in more generality. So in this first example, we'll see that we really only need to know a single base case, and all we need is to know that PM is true, and that implies that PM implies PM plus 1. And so if PM implies PM plus 1, then of course P n naught through PM would imply PM plus 1 as well. So we're not losing anything by only needing one of them, only needing the PM to get PM plus 1. All right, so here's our first example. So this is a famous identity in algebra if you have this polynomial 1 minus x to the n plus 1, right, you know that 1 is a root of this polynomial. You plug 1 in, you get 0. And so 1 minus x should be a factor, and it tells you the other factor here. It's just the sum of all these simple x to the k powers. And we'll show this for n bigger than or equal to 1. So the proof is by induction. So as a base case, we take n equals 1 and observe that 1, so we have on the left-hand side there, we have 1 plus just x to the 1 power, right, and then times 1 minus x. That, of course, equals 1 minus x squared, which is indeed 1 minus x to the 1 plus 1. Right, so that's true. So the proposition is true in this case. And so now assume that the identity is true for n. So let me say k. Use a different letter so it's not confusing. Assume that the identity is true for k. And what we're going to do is look at the identity at k plus 1. So then if we look at the left-hand side of our purported identity when n equals k plus 1, right? So that's the next one in line after k. Well, let's see, we just have to do some computation, presumably. So what I'll do is we want to try to use the fact, so we know the identity for k, right? So I know 1 plus, up through x to the k times 1 minus x, I know what that is. And 1 plus x to the k, that's x to the k is the term right before that. So let me just write that. So we have 1 plus x plus ... plus x to the k plus x to the k plus 1, right, times 1 minus x. And that is 1 plus, I guess I'll be writing this all out, 1 plus x to the k times 1 minus x plus x to the k plus 1 times 1 minus x. And what we know is that our identity is true for k, right? So 1 plus ... up through x to the k times 1 minus x, that equals 1 minus x to the k plus 1. So this is 1 minus x to the k plus 1 by our induction hypothesis. And then we can just distribute that other term. All right, so distribute this here. Minus x to the k plus 2. And we see that we get a cancellation here. And so this just equals 1 minus x to the k plus 2, which of course is 1 minus x to the k plus 1 plus 1. Right, so the identity is true for k plus 1. So the identity is true for k plus 1. Therefore, the identity for n equals k implies the identity for n equals k plus 1. So therefore, the n equals k case implies the n equals k plus 1 case. And so the proposition is proved by induction. Okay, so basically here we have our base case for n equals 1. Okay, so sort of schematically, according to what we discussed above, so we proved the proposition p sub 1, and then we showed here that the proposition pk implies pk plus 1. Right, so P1 implies P2, and P2 then directly, once we have P2, that directly implies P3, and we didn't need P1, right? So just P2 itself is enough to imply P3, so we don't need P1 and P2. So you're allowed to, in the general case, assume both P1 and P2 to get P3, but in this case, P2 itself is strong enough without needing P1. Okay, and P3 itself is strong enough to give P4 without needing P1, P2, P3. Okay, so that's how this this sort of simpler outline that we have. So this proof looks simpler than the general outline we've given up here. So this general outline is much stronger in general than you often need in practice. So here's one where you need more than one base case. We have this proposition. So we're defining a function by f of 1 equals 3, f of 2 equals 3 halves, and then we have this what's called a recursion that tells us the value of the function at the next one if you know at a particular integer if you know the previous two. So we can figure out f at 3 because we know the previous two values. And just so this formula is just the average of the previous two values. Okay, so just average the previous two, that gives you the next one. And then allegedly our general formula comes out to this. So this gives you recursively, but this is not an explicit formula that will quickly give you the answer for a given n, but we can derive this explicit formula from the recursion. So we can prove this by induction. Okay, so note that f of 1 equals 3, which is 2 plus 1, and 1 is negative 1/2 to the 0. And so this is 2 plus negative 1/2 to the 0, which is 2 plus negative 1/2 to the 1 minus 1. Okay, so f of this n is 2 plus negative 1/2 to the n minus 1. Okay, so the theorem is true for n equals 1. And f of 2, that's 3 halves. That is 2 minus 1/2. And that's 2 plus negative 1/2 to the first power. Right? And that's 2 plus negative 1/2 to the 2 minus 1, right? So we have f of n, our n is here, right? F of n is here, n. So that works out. So we have established base cases. Okay, so now we will assume that the theorem is true. Well, we're going to use the stronger form of induction, the full principle stated above. So we'll assume now assume that f of, let's say f of I equals 2 plus negative 1 half to the I minus 1 when I is between 1 and k, and k is bigger than or equal to 2. And k is bigger than or equal to 2. Okay, so far we have this for k equals 2. We know that our theorem is true when for I equals 1 and 2. And then we're going to try to establish it, show that that implies the theorem is true for 3. And then once we have 1, 2, and 3, that'll imply for 4, etc. Okay, so what we'll do is then look at f of k plus 1. Then f of k plus 1. So we're trying to show this. So what we know is this. Okay, so f of k plus 1, that's the average of the previous two. So the previous one is f of k. The one before that is f of k minus 1. And we're looking at the average. And now by our induction hypothesis, that's this hypothesis here, right? We know, so k and k plus 1 are in this range between 1 and k. So we can use this formula. So this formula is now valid. Okay, that's our induction hypothesis. So we have 2 plus negative 1 half to the k minus 1 plus 2 plus negative 1 half to the k minus 1 minus 1, which is k minus 2. And all of that over 2. Okay, and so 2 plus 2 over 2 is 2. So we have 2. And then we have negative 1 half to the k minus 1 plus negative 1 half to the k minus 2 over 2. And we just have to simplify this somehow. So we have 2 plus, we have the 1 half, and we have a common factor of negative 1 half to the k minus 2, right? So we'll have negative 1 half to the k minus 2. And what's left is we have negative 1 half left and a plus 1 here. So that's going to be 1 half. And we have this other 1 half. So that's going to be 1 half squared, which is the same thing as negative 1 half squared. So this is going to be 2 plus 1 half squared times negative 1 half to the k minus 2. And then just insert a minus sign in here. Okay, so you can just insert a minus sign in there. And that gives you your 2 plus negative 1 half to the k. Okay, and I guess is one last thing. That's 2 plus negative 1 half to the k plus 1 minus 1. Okay, so you're so you have k plus 1 here, that goes in there, and that jives with the general formula, how it works. Okay, and so that completes the proof by induction. So the proof is complete by induction. And just as one last little remark, you might, in this principle of induction here, right? I mean, so why is induction true? I mean, so this principle of induction is true because of this little argument here that I outlined, like this cascade kind of argument, right? If these ones are true and that makes the next one true, then if we have and then we just group those, and that implies the next one's true, etc. That's not a very mathematical argument in a sense. I mean, it's a very intuitive, plausible, reasonable argument, but it has a kind of unmathematical, unrigorous feel about it. And so if you want to dig into why induction is true, you find out that, well, really it relies on sort of the axiomatic properties of the natural numbers. So at that point, you're kind of asking yourself sort of hard questions about what we actually mean by natural numbers and how the natural numbers are founded, logically speaking. And the book doesn't delve into this, but the basic mathematical statement that the principle of induction is equivalent to is called the well-ordering principle. And so this is the well-ordering principle. This is the more mathematically sound, more rigorous sounding statement that's basically equivalent to induction. So it says that if we have a subset of the integers which has the smallest element, okay, so if you're picturing the integers kind of left to right, this subset has a left barrier, so it's sort of bounded to the left. Then any non-empty subset of A also has the smallest element. And if you just take a second to think about this seems eminently reasonable, and is really sort of something that comes from the foundation of the natural numbers and the integers. What it really, it's sort of buried in the foundations of just the most basic idea of our understanding of what number is. And that's not really our objective here. So the well-ordering principle is something that generally we could just take for granted as something that seems eminently intuitively reasonable to any sane person. And it might be an interesting exercise for you to just kind of think about how the well-ordering principle implies the principle of induction. So basically, if you take the well-ordering principle on for granted, an argument by contradiction implies the principle of induction. So basically, if your statements that you're trying to prove in an induction aren't all true, then you look at the set of integers where they're not true, and then that's going to have a smallest element, and by this well-ordering principle, and you can see if you can figure out where the contradiction comes from there. Okay, anyway, enough of that digression. So the last concept that I want to review before we're done with preliminaries is the notion of cardinality. So cardinality, it deals with the size of sets, and it deals with it in a peculiar way, because we're used to thinking about size as being correlated with number, right? This set has, this collection of things has 5 elements or 6,000 elements or whatever. But actually, counting and cardinality really goes to something that's more primitive than number. Because even without the notion of number, right, we're just kind of tied up with language, these abstract labels, 1, 2, 3. So even without them, you can tell when two collections have the same number of things, right? So without even counting how many things are in here and in here, I can say with certainty that they have the same size, because what I can do is I can pair off. So these two, this one with this one, and then these two, maybe I should have made a smaller set. These two, I don't know, this could go on like this. Okay, so you see I've used these arrows to indicate that I've set up a correspondence to every element here. I have exactly one element over here, and every element over here gets hit, right? So, I mean, exactly what we've done is we've created a one-to-one and onto function from the green set to the blue set. And so everything in here gets hit. So by this, I'd imagine this the arrow is going this way, or sort of defining a function. So everything here gets hit, so that's our function is onto, and everything here, it gets hit by exactly one element, or we're doing a pairing off. There's exactly one thing over here corresponding to that, so the function is 1-to-1. Okay, so we know these sets have the same size without even knowing what number is associated with that size by the fact that there's a bijection between them. And so let me just remind us of that. Well, there's a 1-to-1 and onto function, which is the definition of bijection. So let me make sure I write that down. All right, so if there's a bijection from A to B is just a 1-to-1 and onto function. Okay, so the image of this function is all of B, and any two distinct elements of A go to distinct images over here. And in this case, we say that A has the same cardinality as B. Okay, so bijection from A to B, A is the same cardinality as B, and we write A is, you can read this as A is equivalent to B, or A has the same cardinality as B. And we write it that way because this is an equivalence relation. Okay, so just a proposition. So this is reviewing something from last lecture, that the concept of equivalence relation. So an equivalence relation is a relation that's it's reflexive, symmetric, and transitive. So reflexive means that A is equivalent to A. So we need to show that A is equivalent to A, or A has the same cardinality as A. We need a bijection from the set A to itself. And the natural bijection is just the one that takes any element to itself. So the function, the identity function on A, which by definition, so this is a function which takes A to A and is defined by, so it takes A to, line this up better. So it takes A, any A in A to A. Okay, so this is a 1-to-1 and onto function. Okay, it's clear. You take any A in A and A goes to it, so it's onto. And if A is not equal to B, then clearly the image of A is A, the image of B is B. Those are not equal, so different things go to different things. So that's 1-to-1. So this is a 1-to-1 and onto function. So A is equivalent to A. Number two is that if you have A, so the relation is symmetric. So if A is related to B, so if A has the same cardinality as B, we need to show that B has the same cardinality as A. So we can, so let's say assume, so we're assuming A has the same cardinality as B, and we need to show that B has the same cardinality as A. So what does this mean? A has the same cardinality as B. So we have a bijection from A to B. F from A to B is a bijection, a 1-to-1 onto function. But we know if we have a 1-to-1 and onto function like this, then we have an inverse function. Well, so then F inverse from B to A is also a bijection. And this is easy. So if so F composed with F inverse, so we have the two compositions, F inverse composed with F, that's the identity function of A, and F composed with F inverse, that's the identity function of B. And it's very easy using these two equations to show that F inverse must be a bijection. So whenever you have F composed with G is the identity function, and G composed with F, so you have this identity of A, identity of B, then it's easy to show that F and G must both be bijections from that. Maybe I'll have you do that for homework, or you can try it for yourself if you're not convinced. So then we have a bijection from B to A, so therefore B has the same cardinality as A. Okay, which it should be, right? If this is measuring this sort of size of these sets, A having the same size as B should be no different than B having the same size as A. And then 3, we have transitivity. We're supposed to have transitivity, so we assume A is related to B and B is related to C. Then we need to show that A is related to C, right? So you can sort of go through B to get from A to C. So that is, we have a bijection from A to B and another bijection from B to C. That's just the definition of these symbols. So those two functions are bijections. And then the obvious thing is to just consider the composition. Then we have, right, do F and then follow a G that takes A to C, and it is easy to show that the composition of one-to-one functions is one-to-one and the composition of onto functions is onto. And it's easy to show that the composition of one-to-one functions is one-to-one and one-to-one functions is one-to-one and onto functions is onto. Okay, that's probably something I'll have you do on homework as well. Or you can just work it out for yourself now. If you care to pause the video, you can always do that. Okay, so we have this, so that means that since G and F are both bijections, the composition of G and F are bijections. I guess that's a simpler way to have said this. If you have two bijections and you compose them, it's still a bijection. Okay, so that's essentially the sort of easy lemma we need here to proceed. So therefore, we have that bijection, so A has the same cardinality as C. Okay, so that's why we're using this tilde symbol, because we have an equivalence relation here. Okay. All right, so for a concrete example here, you may know that the natural numbers have the same cardinality as the integers. So the natural numbers, right, they sit properly inside the integers. So it looks like, z in some sense is bigger than the natural numbers, but in this sense of cardinality, they are the same size. Okay, so they're both infinite sets, and it looks like this one has more elements, but in a way it doesn't. You can put, there's a one-to-one correspondence, so you can sort of count these off in a way that that makes them correspond one-to-one and onto. So basically what we can do, what we can do is take the, say, the non-negative integers, and we can send them to the odd natural numbers, say, and then we can take the negative integers and send them to the even numbers. So you can do something like, so define a function from z to n by, so f of some integer n. So let's say if it's odd, it's going to, or sorry, if it's non-negative, so when n is bigger than or equal to 0, we're going to send it to 2n plus 1. Okay, so 0 goes to 1, 1 goes to 3, 2 goes to 5, etc. So we get all of the odd natural numbers, and when n is less than 0, we want to get all of the even ones, so we need, so we'll just multiply this by 2, but it's n is negative here, so we'll just throw in a minus sign. Okay, and it's pretty easy to argue that this is going to be one-to-one and onto. Yeah, I mean, it's onto, we're hitting all of the odds, we're hitting all of the evens. and it's 1-to-1 because none of these, so any two different things here, right? If the two different things, if one is positive, one is negative, well, they clearly don't have the same image because one is even, one is odd. If they're both positive or both non-negative, this thing has a positive slope, right? So it's this linear function has a positive slope. So, I mean, it's easy to just go by the definition, right? So if 2n1 plus 1 equals 2n2 plus 1, right? So if this function, if you take two non-negative n's, they give the same image. You can just solve this. Whoops, I don't know what I did here. You can just see that this implies that n1 equals n2. Right, so stuff like that. Okay, so kind of boring, but you can show that that's 1-to-1 easily. Okay, so we have a bijective function from the integers to the natural numbers. Here's another example of a proper subset having the same cardinality as the full set. So this finite interval here in the real numbers has the same cardinality as the real numbers. And so what we can do is you can imagine some kind of, right, you can just imagine the graph of this function. Try to think of what the graph of a function that would establish a bijection between this set and the reals would look like. So you have to hit all of the reals, right? So it has to go from negative infinity to positive infinity over this interval. So you'd imagine something which has, say, asymptotes here at -1 and 1. Okay, so some kind of function maybe that would look like this, something like that. And something that has asymptotes at 1 and -1. So for example, you can take 1 minus x squared, put that in a denominator. Right, so that's going to blow up to infinity, negative infinity when you go to 1 and -1. And well, this function here is not a, this function here is not the right one. It's an even function, so it wouldn't look like this, but you can easily make it an odd function by just changing that 1 to an x. Okay, so f of x, which is that function, is a bijection. Is a bijection when it's defined, so the x here defined in the interval from -1 to 1. And it's going to hit all real numbers. And that's a relatively simple exercise. The book, uses the negative version of this function and then says that you can use calculus to show that this is a bijection, but actually you just need basic algebra to show this is a bijection. So you might like to try that for yourself as well. Perhaps, again, I don't know, maybe I'll assign that for homework. Okay. Now I want to recall some terminology. Largely this terminology is to deal with infinite sets. So you may know that there are different infinite cardinalities. And so we'll review the argument that the real numbers have a different cardinality from the natural numbers. Okay, so we need some terminology to deal with this situation. So just some basic definition. A set is finite if it has the same cardinality as the first n natural numbers for some n in the natural numbers. A set is infinite if it's not finite. Okay, so if there's no bijection with any one of these standard finite sets, then it's infinite. A set is countably infinite if it's in bijection with the natural numbers. So this is sort of you should think about this as like the first infinity you come to, right? I mean, you have all the finite subsets, 1 through n in the natural numbers. Then as n goes to infinity, you get this whole set, and you sort of run into the first infinity, this kind of smallest infinity. And then we'll say a set is countable if it's finite or countably infinite. And I should mention the book, I think, regrettably uses the word countable to mean countably infinite. So I'd like to retain a difference, a distinction between countably infinite and countable. Okay, so if you can count your set, it's either a finite number of things that you're counting or sort of an infinite number of things you're counting in a list, like the natural numbers. And then a set is uncountable if it's not countable. Okay, so this would have to be an uncountable set, would have to be an infinite set, which cannot be put in a list like the natural numbers. Okay, so I've already said it a couple of times, but I just want to make a formal note here that a set S is countable if and only if the set can be put in a comprehensive list. Okay, so all of the elements can be written linearly in a list like this. If it's a finite countable set, then the list terminates. Otherwise, it goes on forever. But eventually, somewhere on the list. But if you pick out any element of your set, eventually you're going to run into it at some point. After a finite amount of time. So pick any element of your set. If it takes you a second to tick off each one of these, you only have to wait a finite number of seconds before you get to any particular element that you picked out. And the reason for this is that, this list here tells you a bijection with the natural numbers between your set and the natural numbers. Right? Because this element A1 of your set here, you can just think about this as the image of 1, some function from the natural numbers. The image of 1. So A1 is equal to f of 1, and A2 is equal to f of 2, A3 is equal to f of 3. Okay, so a list is really just a way of specifying a function from the natural numbers to your set. And so a comprehensive list, and that would be a one-to-one function from the natural numbers to your set. And then a comprehensive list would just be an onto one-to-one function. In other words, a bijection. Okay, so this is really a convenient way of representing this bijection between your countable set S and the natural numbers without having to be overly formal and pedantic about it. So to see why this is so convenient, this list technique for exhibiting a countable set is this proposition that any subset of a countable set must also be countable. And the way you can see this is proof. List the elements of our set S. So list the elements of S. Okay, so S is going to be, let's say, S1, S2, S3. Right, so we get all of the elements in this list. The subset A is gotten by just deleting elements off this list, right? So just deleting particular entries in this list. So the subset A is obtained by deleting entries from this list. And one way to be a little bit more formal about this is to write, the thing you're deleting is just the complement of A, right? Everything that's not in A in the set S, which by definition is just the complement. So since A is equal to the complement of the complement, right? So it's equal to the elements in the set that aren't in the complement of A. Okay, so A is you take the set S and you kick out all the things in the complement. Okay, well, so if you delete, but the thing is if you delete things on this list, you're still going to have a list, okay? So if you delete everything in the complement, you have all the elements of A, but now they're on a list. But deleting entries on a list, a list is still a list. So A is countable. Okay, admittedly, this proof sounds a little bit unmathematical. We're talking about lists, and it is possible to be more pedantic, put this in terms of bijections, defining a bijection. It's really, I don't think, worth the extra effort. I'd rather us save our energy for when we get to the real analysis. This is supposed to be a bit of a review anyway. So, and anyway, this seems like a perfectly I don't know who would argue with the logic of this proof. Anyway, okay, so any subset of a countable set is countable. So the next proposition says that if you have two countable sets, multiplying those sets together, taking their Cartesian product, still yields a countable set. Okay, so in the sense of cardinality, you can't get a bigger set by multiplying together two countable sets. And so the proof is like this. So A and B are countable sets. So A is A1, A2, A3, right? You have a comprehensive list. B is B1, B2, B3. You have your comprehensive list there. And then, so A times B, we can visualize that as sort of matrix in a way of the pairs of elements here, right? So the ij entry would be a I b j, right? So we'd have a1 b1 a1 b2 a1 b3, etc. Have A2B1, A2B2, A2B3, A3B1, A3B2, 3B3. I could have just paused the video and done this. Okay, so this is the visualization of the set A times B, right? And then we can create a list. So then we can create the list. What you can do is you can, let's see, yeah, you can go diagonally like this. So if you were to go straight across, try to go straight across, right, you'd never get to the end of this. You started writing these down as your list, you'd never get to the end of this row and be able to start the second one. And same in the vertical directions, but what you can do is go diagonally. So you're going horizontally and vertically at the same time. So then you can go like this, right? And so you can create the list A times B, then is A1, B1, A2, B1, A1, B2, A3, B1, A2, B2, A1, B3, and then etc. Okay, going on like that. Kind of the pattern is what you're putting down in this first one here is the indices, the 1 and the 1, they add up to 2. That's the only pair of indices that add up to 2. And then you have the two pairs of indices that add up to 3, 2 plus 1 and 1 plus 2. And then the ones that add up to 4, 3 plus 1, 2 plus 2, 1 plus 3, and so on, right? So you're really you sort of have chunks here where the indices add up to 1, where they add up to 2, where they add up to 3, or they add up to 4, right? And so you could actually use this to really write a more rigorous kind of proof, creating a bijection between the natural numbers and A cross B. But I think the idea is clear enough that this works. So that shows that the product is countable. So one of the first surprises about cardinality is possibly that the natural numbers that the rational numbers are countable. And so the rational numbers, if you think about them in the real line, seem so much more numerous than the natural numbers, but they really aren't in the sense of cardinality. And this is actually not a very hard proof now that we have the previous two little propositions at our disposal. So any non-zero rational number can be uniquely written as P over Q, where P is an integer and Q is a natural number. So if our rational number is negative, we absorb that negative into the numerator, and then the denominator we can always take to be positive. This breaks down when you have zero, right? Because zero is zero over anything. So that kind of is a little bit annoying. And what we can do is use this to create a function. So it can be uniquely written as that. So define a function from the rationals to z cross the natural numbers by f takes f of p over q is equal to p comma q, and f of 0 is equal to, let's say, 0, 1. Okay. So this function is 1-to-1. Okay, so it's 1-to-1 by the uniqueness here. And so the uniqueness of how you can write rational numbers that way. So f is 1-to-1 by the uniqueness quoted above. It is not onto z cross n. So it's not onto because the only thing with 0 as first coordinate that's hit is this 0 to 1, 0, 1, comma 1, right? 0, 2 is not hit. So it's not onto, but this is it is an onto function onto the image, okay? So it's not onto z cross n, but it is onto as a function from q to just f of q. Okay, so you can always make a function onto by just restricting your attention to the image of the function. So redefine the codomain of the function to be equal to the image. So therefore, thus q has the same cardinality as f of q, right? So this is a bijection from q onto its image, and this f of q is a subset of z cross n, and z cross n is a product of countable sets, and a subset of a countable set is countable. Okay, so thus q has the same cardinality as f of q, and f of q is countable as a subset of a countable set, since the product of countable sets is countable. Okay, so we're using the previous two propositions. So since the product of countable sets is countable. Okay, so that means that Q is countable. So it's the same cardinality as a countable set, so it's countable. Okay, and I guess maybe I should say countably infinite to be a little bit more descriptive here. Of course, the rationals aren't a finite set. We know that. Okay, now one more proposition about countable sets. Okay, so this proposition says, suppose we have an indexed family of countable sets. Okay, so we just have a bunch of sets. They're all countable, and they're just labeled using elements of some other set. But suppose the labeling set is also countable. Okay, so we have a countable number of sets which themselves are countable. And then the union of all of those countable sets is also countable. Okay, so even you have this, or you might think this could be one way to get a larger set is to take, sort of an infinite number of countably infinite sets, but if that infinite number of countably infinite sets is itself countable, then the union is still going to be countable. Okay, so for the proof, so list lambda, so the set lambda is lambda 1, lambda 2, lambda 3, etc. So our sets, right, so if our lambdas are listable, that means our sets are listable. So we have A lambda 1, A lambda 2, A lambda 3. Okay, and in this first A set, so I'll have A1, 1, A1, 2, A1, 3, etc. Okay, so we can write out our sets this way and then write out all the elements in the sets this way. Okay, so our first set, we always have the 1 first. The second set, we always have the 2 coming first. Third set, 3 comes first. All right, and then we can create a list here in the following way. It's the same type of thing we did before. So you go diagonally like this. And now these sets can have things in common, right? So A1, 2 here might be the same thing as A3, 1 down here, but then you just skip it when you're going along. Okay, so then you can create a list. So create a list. Create a list by going diagonally and skipping repeats. Skipping duplicates. Okay, so that shows that's the union then. All right, so the union is just dumping all of these things together in one collection. All right, so we represent that whole union by going through them in this way. And so that union is countable. Okay, now we come to a really famous proposition, which probably really shocked the mathematicians of the day. And this is due to Cantor, that there is no surjective function from the naturals to the reals. In other words, and so a function from the naturals to the reals is just going to be a list, right? Well, yeah, so it would just be creating a list of real numbers. And so any such list is going to fail to hit at least some real number. Okay, so at least some real number which is not hit by this, which is what it means to be not surjective. And so therefore these sets have different cardinalities. Okay, so you have two different sets and they don't have the same cardinality. And the method of proof is famous. It's by what's called the Cantor diagonalization argument. So this is Cantor's diagonalization. Okay, and so here we haven't yet discussed in any really logically sound fashion, we haven't examined our assumptions about the real numbers, but basically we're just taking the real numbers are, numbers that can be written as decimals, okay? And so that's the understanding of the reals we're working with here. So here's how the proof goes. So let f be any function from the naturals to the reals, be any function. Okay, then we have a list of real numbers. So we have f of 1, f of 2, f of 3, and we can write them out just like so, okay, as decimals. So this is an integer, and then we have the decimal tail, integer decimal tail. And so what Cantor does is draw our attention to the diagonal starting on the decimal place. Okay, so you look at this this diagonal here. So define the real number r, which equals r1, r2. It's going to be a decimal number. Start at decimal point r1, r2, r3, etc. By r sub I. So basically, you're just going to make it different from, so it's going to be different from f1 in this place, it's going to be different from f2 in this place, it's going to be different from f of 3 in that decimal place. And so you can just make up some rule that always does that. So say, if the place that you're looking at, it's not equal to 2, then r, then the decimal for r at that place will be 2. And if it is 2, then make it 3, say. So Ri, it's going to be 2 if a sub I is not equal to 2, and it'll be 3 if a sub I happens to equal 2. Now, basically the idea of the argument is that we've made this real number so that it doesn't agree with the ith thing on this list here in the ith decimal place. So if it disagrees with it in a decimal place, then this r can't be that, right? So if r disagrees with f of I in the ith decimal place, then r can't be f of I, and so r is not f of I for any I. The only slight wrinkle in that argument is that the decimal representation of a number isn't necessarily unique, because for example, if you have any decimal that terminates after a finite number of places, right? So say something like like 0.53, that's the same thing as 0.52999, right? So any finite decimal, in other words, any decimal with a infinite string of zeros after it, you can change it into a decimal with an infinite string of nines after it by changing this, right? So these two things look very different, but actually they're the same. So your decimal representation isn't unique. Just knowing that, right, these two things are the same, even though they differ in almost every decimal place. So just knowing that two real numbers differ in a decimal place doesn't necessarily say that they're not the same. But it's not hard to really to make the argument airtight, taking this into account, because this number we're defining here, this crazy string of 2s and 3s, definitely isn't any real number like this. Right, so if you have a real number like this on this list, this thing isn't it. And if any one of these is a non-finite real number, then it's going to have a unique decimal representation. And so this real number you constructed is not it, for the reason we outlined. So it's easy to see. See now that R does not equal f of I for any I. So f is not surjective. Okay, so that shows that the real numbers are not countable. Okay, so we have an uncountable set. And in fact, there's an interesting argument, I think, also due to Cantor, that shows something even more fantastic. So if you believe that there's two different kinds of infinities, countable ones, and then this infinity, size of infinity represented by R, you're probably going to be willing to believe that there's ever bigger and bigger infinities, and that is the case. So Cantor had showed a way to see that by proving what's called Cantor's theorem. So they just remind you a little piece of terminology. So a definition: if A is a set, the power set of A is the set of subsets of A. Power set of A, which is denoted by P of A, is the set of subsets of A. Okay, so example, if A is equal to 1, 2, then the power set of A, and so the empty set is a subset. Okay, so we're constructing this new set, so we start constructing a set, and the elements are subsets of my set. Okay, so we have the empty set as a subset, the set with just the one element 1, the set with the one element 2, and the entire set itself are all elements of the power set. Okay, so those are all the elements. So what Cantor showed, so Cantor's theorem, is that there's never, so any function from a set to its power set fails to be onto. So any function from set A to its power set is not onto. And the proof has a very similar flavor to the proof of the previous proposition. It's a very, very similar idea. So I thought I'd show you this as well. So let f be a function from A to the power set. And what we need to do is somehow construct a subset of A. An element of the power set of A is a subset of A. So we need to construct somehow a subset of A, which is not hit by this function. And it seems kind of weird. I mean, it doesn't seem like there's a lot of information here. And so maybe it's not apparent exactly what to do. But what we do is we're going to look at this function. It takes elements of A to subsets of A, right? So to each element of A, f of A is a subset of A. Okay, so for any A, for each little a in big A, f of A is a subset of A. And therefore, this subset either contains A or not, right? So either A is an element of this set f of A, or A is not an element of f of A. So what we want to do is we're trying to create some subset of A, some element of the power set, which is not hit by this function, right? So we want to we're trying to create some set B, some subset of A, we'll call it B, which is not equal to f of a, right, for all a. So for all a and a. And the basic idea about how you do that is you make this b disagree with f of a about membership of the little a here. So if a is in f of a, we'll make sure that a is not in b. And if a is not in f of a, then we'll make sure that a is in b. Okay, so then these won't be the same set. So let's just review what I just said. So we're going to make this set B we're trying to construct disagree with this set which is in the image by one element, right? In particular, this element A. So we'll make them, so if A is in f of A, right, then we'll make sure that A is not in B. Okay, so that would ensure that these sets are different. Okay, so if A is in f of A would not be an element of B. But if A is not in f of A, then A will be an element of B. Okay, so in other words, the things that get put in B are exactly the things, the elements in our set, which are not elements of their images. Okay, so that's how we're going to define this set B. So what we're doing is we'll create a set B, so we create a set B, which is a subset of A that disagrees with each f of A about membership of A. Okay, so that's the main idea. So B, you're only going to put A in B as the set of A in A such that A is not an element of its image, f of A. Okay, and so now you just have to run through the details. All you have to show is that B is not in the image of this function. Okay, so then B does not equal f of A for any A, little a, in big A. Okay, so why? Let's just run through the reasoning, make sure we're clear about this. So there's only two cases, and so there's two possibilities. Either A is in f of A or A is not in f of A. If A is in f of A, then by definition, A is not in B. So then A is not in B by definition. So f of A doesn't equal B, while if A is not in f of A, then A is in B. So again, f of A is not equal to B. Right, so we just enacted our idea, just showing that the reason these two sets aren't equal is because they disagree about the membership of A. If A is in f of A, it's not in B, and if it's not in f of A, then it is in B. Okay, and so that completes the proof. So this completes the proof. Okay, and so what you can do with this proposition is, given any set, right, say like the natural numbers, then you have the power set of the natural numbers, and you have the power set of the power set of the natural numbers, and the power set of the power set of the power set of the natural numbers, right? And so this sort of goes up and up and up like this. There's no onto function here, no onto function here, no onto function here. And so these sets intuitively are just getting bigger and bigger and bigger. And even more surprising fact is that if you do this, this doesn't exhaust the sizes of infinities. There's infinities that sort of aren't on this list here. which would be something you could explore in set theory. And as just a by the way, this power set of the natural numbers actually has the same cardinality as the real numbers. And one way you can see that, an easy way you can see that is that what you can establish is that it has the same cardinality as the set 0, 1. And that has the same, any two intervals in the real numbers, it's easy to establish a bijective correspondence between them. So this has the same cardinality as -1 to 1, which we showed earlier had the same cardinality as the real numbers. So you can show this, you can represent every number in here in binary, right, which is zeros and ones. So you just have binary sequences, A1, A1, A2, A3, where all the AIs are 0 or 1. Okay, so you represent your numbers in binary. And then what you can do is think about these. So if A1 is 0, so you can interpret this binary string as a set of instructions for constructing a subset of the natural numbers. So if you have a 0, then if this A1 is a 0, that says that you can interpret that as saying that 1 is not going to be in the subset that you're constructing. Whereas if A1 is 1, then you will put 1 in the subset you're constructing. And then you move to A2. If it's 0, you don't include it in the subset. If it's 1, you do. A3, right? If it's 0, you don't include 3 in the subset. If it's 1, you do include 3 in the subset. And you can build subsets of the power set of the natural numbers this way. So that's the indication of sort of the main idea of an argument you can make that the power set of the naturals is the same thing, has the same cardinality as the reals. Okay, I think that brings us to the end of the lecture. So in the lectures next week, we'll get into the real stuff, the real material as in the material about the real numbers. Okay, so we'll start properly talking about analysis in the next lecture.